time you need, identify your zones of interest, identify whatever problematic or some data issue you see, if you see any, and then write your notes, and whatever results you should be getting eventually should reflect the notes that you have taken. And for example, in this log here, from this plot here, I can see that that I have, for example, Shale zone in zone C. I can identify that the upper part of zone D is practically my hydrocarbon zone from experience or from their log response. For example, I can see some flat gamma ray. I can see increase in resistivity. I can see the separation between the neutron and density. And hence, before I even start delving into the software, I know that this is my pay zone, this is my zone of interest, this is the transition zone, this is a water zone. Zone E is practically Shale zone. So you need to identify all of these. Here are, and again, here are some few QC things that you need to look after when you do real formation evaluation. And then you can, I mean, the software is practically some data entry you will need to, anyone can do. And it will give you the results eventually. So here are some tips, like check for spikes. Spikes can mean anything. It can mean bad data transmission. It can mean some bad hole intervals. It can mean some issues with your data. Also check if you have gaps in your data and fix that, whether through interpolation or spline methods or any advanced software that fill your data gaps. See which zone are affected by your bad hole conditions, because whenever you drill, you will always encounter some washout, some zones with mud cake. So you need to identify these zones, and you need to make decisions about how you will fix them or how you will treat them during your formation evaluation. And one final thing, we always assume that the data that comes from the field through the wireline engineer or the LWD engineer is environmentally corrected. This is the case. It's true, this is the case. But there is no harm in redoing the environmental corrections, just in case the field guy missed any correction or anything. So you can redo the whole environmental corrections for every tool in the software, and then you can compare with the field data to see if there are any differences. Again, the quick look is the technique that you will need to take to decide your data based from you looking at the log. It's exactly what I did now when I told you that the upper part of zone D is my hydrocarbon zone. I just looked at the data. I saw a separation, and this separation, practically I have the neutron reading less than the density, meaning that I have some hydrogen index of hydrocarbon effect on the neutron. I have increase in my resistivity. Let me just change the pointer here to see. For example, I have increase in the resistivity. I don't have any Shale zone, so this is this must be my zone of interest from a petrophysical point of view. And this decrease, meaning that I'm transitioning into the water zone below the oil zone. And this is my this shell here, the spiking gamma ray and the neutron, meaning this is my cap, the trap, or what we call the trap. So this is the quick look. You need to look at your log and identify what you will want from it, and then the software will help you achieve it. I know a lot of experienced petrophysicists that just take the data, put it in inside the software, and then take whatever output that they get. This is, no matter how much experience you are, this is the incorrect way. Point blank. Because you see, if you do that, and then you will have some issues with the data, then it will be very painful process to track back what causes the issue in the first place. So take your time, do your QC properly, then you will see that the software is practically some data entry and any middle school child can do, to be honest with you. So here are some, as I mentioned, I will not go through the whole data response, data physics, or measurement physics and how they will respond. So I just put this one here clearly, just to highlight some of the responses that we should be expecting from the gamma ray neutron density whenever we are looking at the data. For example, in shale zones, we will see the neutron going high, the gamma ray is going high, because the radioactivity of the shale will affect the gamma ray, making it reading higher than usual, and the chlorine absorption will be at higher levels, so you will see very high neutron reading. That's an example. Another example is your hydrocarbon zone. Whether it's a gas or oil, you will see a neutron density separation where the neutron will be reading less than the density, and so on. So these are basics. Everybody should know these before taking their first step into the formation evaluation software. So this is it for a small introduction. Next, we will start with the software things. I will present some slides, then move to Techlog, do the workflow that is mentioned in the slides, then go back again, just cover the advanced petrophysical analysis, and then go back to Techlog again. And in the meanwhile, if you have any question or any concern or anything you want to ask me, do not wait for me to finish talking, then ask. I would really much prefer if you ask me at any time and make this presentation interactive. To be honest, I really hate it when I just talk to an empty screen and I'm not really knowing if you guys are listening to me or not. So feel free at any time to stop me and ask me whenever you have any question. So, okay, first part is the conventional log analysis, quanti. Quanti, or the conventional log analysis, is practically what they taught us in schools or university, to be more specific. It's the method where you take your data and you start calculating step by step from the volume of shale into porosity and finally into saturation. It's also called the deterministic log analysis, or the deterministic formation evaluation. So what you will do here, you take your data, you QC it, you finish QCing. After you finishing QCing, you doing whatever data treatment that is needed. If you need to identify bad zones, do some environmental corrections, do some mud calculations regarding the resistivity of mud cake, resistivity of mud filtrate, and so on. Then you take your gamma ray, you apply the gamma ray equation, or you apply the neutron density cross plot. You calculate your volume of shale. Then after which you will take off your density log, neutron log, sonic log. You apply your porosity equation. You calculate your porosity. You take your porosity and your V shell to calculate your effective porosity, and eventually you just apply Archie equation. You evaluate your Archie parameter, the AMN and the RW, and you will get your saturation. That's it. If you know your equation, you are practically doing this equation in the software, and that's about it. This is what we call the deterministic approach. Or it's called, in Techlog we call it the quanti. This is just the module name. It means nothing. So let's go for these steps one by one. The first step here is the QC, or the pre-computation. You can do various types of QC here. For example, you can redo the whole environmental corrections to check if the environmental corrections are done right in the field. Second of all, you can see your first of all, most of the tools that we run inside the borehole are standoff tools, which means they have to be in touch with the borehole to make sure that the source is, whatever source is sending is going to the formation, whether we are talking about a neutron source, gamma ray source, or whatever. So whenever we have a bad hole or washout zone, the contact between the formation and the tool, it will be affected. So we will have a poor contact. We say that we have a poor contact. So we will have a couple of, we can see, for example, the caliper reading high, or this standoff measurement reading higher than usual. So we can use this standoff indicator and the caliper to highlight the zones that are affected, the bad hole zones. So this is one step to identify my poor zones, or the zones where I have the data affected, and then I can take action accordingly. We can discuss the actions in a later steps. We can also recompute the mud properties again. We can use the temperature and pressure measurement to convert the resistivity of mud filtrate and mud cake from the surface into the downhole conditions. So practically these are the things we can start with. And whenever we are ready, we can go ahead with the shale volume. So for calculating the shale volume, the most common methods here are the gamma ray and the neutron density cross plots. The gamma ray uses this equation. I hope I think it's blurred a little bit, but it's gamma ray minus gamma ray minimum, or the minimum readings of gamma ray, divided by maximum gamma ray, or the shale gamma ray, minus the gamma ray minimum. And we can, this equation will give me the eventual volume of shale. This is example of how it reads and how we identify this. So we can use this to identify the shale, and we can also use the neutron density cross plot. We just need to identify the endpoints of for each measurement. For example, the reading of the neutron in 100% matrix, which should be 0, for example, or the reading of the neutron in 100% fluid, which should be 1, and then my neutron measurement in shale. And similarly, we take the similar things with the density, and depending on when the data is falling in the neutron density cross plot, we can also use this to identify the shale volume. So we have different methods. We have also a lot of different methods to calculate the shale volume. And eventually, I can also use a lot of methods, and then I can average whatever methods I like, using a lot of averaging methods, like if I take the arithmetic mean, harmonic mean, median, minimum, whatever. All these methods are available. And if I want to just take different approaches or different methods and then apply them, or eventually averaging my V shale. And if I don't want to average, I can just go with my gamma ray, or for example, from gamma ray or from neutron density. That's it will be up to the petrophysicist or the interpreter to decide which methods they want to use. Similarly, we have the porosity, and for the porosity here, we will have a methods for total porosity and we will have a methods to do the effective porosity. What you will care about is the effective one, because it will reflect your production capabilities eventually. And similarly, you have the neutron density cross plot, the chart to calculate your porosity. You have the neutron sonic, you have the standalone density measurement, you will have the standalone sonic measurement, and so these are the most common. You can use multiple methods, then average, or you average these methods in some way or another. A small tip here, what we like to use here in SLB as an example, we usually use the neutron density in the good zones, and whenever I have a bad zone where the neutron density measurements are invalid or affected by the poor borehole conditions, we tend to use the sonic there, because the sonic will have higher depth of investigation. So that's just a small tip here. Again, the method or the software that we are, the way we calculate the porosity is just a data entry, pure data entry. We just take the data, we just take it and put our inputs, and that's about it. And similarly, we have this slide, which we already previewed in the introduction part, so I will not take much time here. After the porosity and the shale volume comes the most important part for the petrophysicist, which is the saturation. That's because the saturation will eventually leads you or tell you, this is my oil, this is where my oil is, or more importantly, this is where my producible oil, and then I can take whatever results, send it to the operation to do whatever subsequent operation they want to do. They want to perforate these zones, start producing or whatever. So we will need to finally calculate the saturation. Of course, the saturation depending on the which resistivity we can use. We can use the shallow resistivity to calculate the SXO, and you can use the deeper resistivity to calculate the SW, which will represent this formation. So, sorry, okay. So we will have different methods here to calculate the saturation, like RT, which is the most common or most popular way to calculate the saturation. And in some cases where we have dispersed shale within the formation, we can have different methods, like the dual water, Waxman-Smith, Indonesia, total shale, and so on. In Iraq environment, we usually go with RT. That's the main thing. And here in Kurdistan, it's a bit more complicated, so we use even more advanced methods to calculate the saturation, like the dielectric or some more advanced tools. So this is RT. What we will need to do here for RT, aside from taking the input from the previous steps, like the porosity and whatever resistivity measurement, we will need to identify the RT parameter, which is the AM and N and RW. And we can do this by utilizing what we call a picket plot. Picket plot is practically the porosity versus the resistivity. And what we will need to do is identify a water zone where we will have a 100% water, or in other word, 100% water saturation. So we will have a water saturation identified. We will have the porosity from the previous methods calculated. We will have the RT known, because this is practically a tool measurement. So we will have AM and N and RW as unknown. So what I will need to do here is either assume the A, M, and N are the default value, which is 1, 2, 2, and use these to evaluate the RW, or if I know the RW from core or from whatever methods or field knowledge or previous wells, if I know the RW, if I know the value, I can use it to identify the A and M. Because you see, what I would like here is when I take my zone of interest, the water zone, if everything align, my line here, the 100% SW should match the data. So whenever I get a match, it means that my parameters are correct. I will go, yes, Muntazar?
Yes, sir. I have a question, please.
Yes, please go ahead.
This 4 line in the plot, do you justify it or to get the right parameter, or it's by default?
Okay, so this line will move. They are not fixed. They will move based on whatever values of RW or AM and N you put in the input, in your input. So, and this cloud here for this cluster will represent your actual data. So what you will need to do here is practically match the 100% line, which is the first one, with your 100% SW data or your water zone. Whenever you get the match, then that's about it. So these lines are not fixed. They are practically your modeled, let's say, your modeled line or your saturation equation. And you will just need to move it, move your Archie parameter to get a match with your actual data. Well, we will see it. We will see how to use it in the software in the next steps. So this will be your inputs. Formation resistivity, this is a log reading. Your porosity, which is the whatever you evaluated from previous steps, and this will be your outputs. You cannot. I mean, there's no way you can solve for all of these 4. You have to know one of these. For example, you will have to either assume that the A, M, and N are default and evaluate the RW, or you should know the RW from, I mean, usually the client, they know, they have their core, they have their internal studies. And if they give us the RW value, we can use these to optimize the AM and N. So it's one way or another. We cannot evaluate all of these. So this is the part where I will. Okay, just a minute. Do you want to keep discard? Okay. This is the part where I will move away from the slides and go to Techlog. So please confirm if you can see my Techlog screen.
Yes, we can see it clearly.
Okay, good. So I am not really sure how proficient or how familiar you are with Techlog. It's practically, we called it a borehole platform, which means that we use it to do a different type of borehole calculations that start from petrophysics into geology, geomechanics, reservoir, geophysics, and so on. So it practically have everything that you will need for all the majors or a PTE needs. In this window here, which called the project browser, this is where my data is. This is practically my well folder, and inside of the well folder you will see a lot of data sets. We call these data sets, and every data set will have different type of data. For example, you can have your open hole logs here. If you can have your PLT logs in another data sets, you can do different section, and every section will have its data set. You consider it of a folder. And inside of every data set, you will see a lot of measurements from open hole into zonation, into index data set. This is MICP. zones, and so on. As a petrophysicist, well, what you will need, or what you will need to do first, as I mentioned, is plot your data. To do so, I have this tab here, which is called the plot. It will have different type of plots that I can use to check quality control and see whatever I need in my data. For example, I have the log view, which will open an empty window from which I can go to my data set or the working data set, and I can start with displaying whatever data I want to see. For example, let's make a triple combo or basic log, starting from gamma ray. So this is my gamma ray here. And I can view logs by just drag and drop them into their respective window. So gamma ray, and I will also want to see the caliper. Okay, this is my caliper. I also want to see my resistivities. Okay, okay, this is the resistivity medium, and this is my deep resistivity. If you are not sure about any of these namings, because I know most of these names because I worked on this dataset multiple times, so I memorized them. You can check the family and you need to know which measurement you are looking at. So for example, now if you do not know what D bar mean, you can just look at the family. It mentioned resistivity dash deep. So this is my deep resistivity. And the unit is ohm meter, so we are good here. I would also want to see my neutron density. So let me see, where is the density? Dense, okay. This is density. This is my neutron and the sonic. So that's my logs. I also want to see the zonation. So I will add the zonation track, and let me add the zonation stratigraphy. So now I have a log here. One final thing I would like to do here is change the scale here. 26. And this is my triple combo right here. So we have zone B, we have multiple zones, and we have also the zone E. Okay, and we have neutron density. Let me because I would like to, let me just move the sonic because I would like to see the neutron density in a more clear way. So this is the first step. Now I'm looking at my data, and I will need to identify, this is just to show separation. I need to identify my zones. So let's start from, this is the gamma ray, this is 7, okay, this is a baseline for gamma ray, okay. And that's my caliper here. Okay, so if we look at zone C, we can see that my gamma ray is going crazy high. Not crazy, but it's a bit high. My neutron is practically reading 50% porosity, which is not physically possible. And I have very low resistivity. So zone C is Shale zone. That's about it. And if I look down into zone D, I will have this separation between the neutron and density, where the neutron, if I go calculate the porosity from density and go back, look at the neutron, compare the porosity to the neutron, I will find the neutron porosity reads less than the density porosity. This is practically the hydrocarbon or the hydrocarbon effect on the hydrogen index of the neutron, which will mean that my neutron will read less than the density in hydrocarbon zones. Now, how can I confirm if this is practically a hydrocarbon effect or just a change in lithology? So this is the limestone scale. So if I have some change in lithology, like sandstone, or if I have dolomite, it will, I mean, the response will not be a much. So if I look, what I need to confirm that what I need to do to confirm that this is my hydrocarbon zone is practically looking at the resistivity. So my resistivity here is going higher, meaning that I am truly in a hydrocarbon zone, and I am also in a clean zone or a clean rock in term because the gamma ray is not reading very, a very high reading, indicating that I have no shale here. So this is my hydrocarbon zone. And below my hydrocarbon zone, this is transition here, I am having this is my water zone. So you know how the reservoir is going, that you will have your water. Above your water, you will have your hydrocarbon. And above your hydrocarbon, you should have a trap to prevent the hydrocarbon from migrating further. So this is a standard reservoir here, where I have my water zone, then I have my oil zone, and I have my cap here. So I can just use this plot to highlight my hydrocarbon zone. Starting from, this is my hydrocarbon zone. This is my cap. And practically whatever below it is my water zone. So you see, I spent some time just before I jump into the whatever quantity that is available, and before just jumping and blindly calculating V-shale, blindly calculating porosity, and blindly just doing an Archie equation, because as I mentioned, this will be your most important part to do. One more thing I can use also to cross-check my data is the cross plots. I have here cross plots, histogram, box plots, and different type of plots. So I can use my cross plot also to bring the neutron. And again, what is the density? Density. This is my neutron density cross plot. Okay, cancel. And okay, let me bring the gamma ray too. I would also like my gamma ray too. Okay, and this is my I just opened the cross plot. I dropped my x-axis, y-axis. I used the gamma ray to color my data distribution. It will be important to identify which data are affected by high shale and which data are not affected. And then you will have your chart, which are practically whatever you see in the Schlumberger chart book, Halliburton chart book, or Baker Hughes chart book. So these are charts for every tool that you will have in the industry. So all you will need to do is identify your service company or the company that doing the logging and which tool they are using. And whenever you are, then you can use, whenever you know which one, you just select it, double click, and this is my data. So now if you see, this is my neutron density cross plot, this is my sandstone line, this is my limestone line, and this is my dolomite line. What I would like to see here is where is my data distribution is at. So this is my data distribution. It looks messy, to be honest. I cannot tell which one is which. Is it dolomite? Is it limestone? Is it sandstone? So the first thing I can take here is see the distribution of the gamma ray, because if you remember, I use the gamma ray to color my data distribution and use the scale from 0 to 150. So whenever I have a darker shade for my data, it means that I'm in a clean part or the clean rock. And whenever the data distribution goes or the data coloring goes lighter, it means that I have a shale here that is moving my data. So I can either go and add a filter, define a filter. So I will just tell it filter gamma ray below, let's say 75. Okay, I think I still have one. Let's modify it into 60. You see now, all the high gamma ray data, just went away. And most of the data distribution that is left is practically between the sandstone and limestone. I can use this, for example, or I can go to my zonation tab, select the stratigraphy, and look at it at a zone by zone basic. So, for example, we said we suspect our hydrocarbon in zone D. So let me go back and just pick zone D. Zone D is practically sandstone with some limestone from here and there. So I can just look at it on zone by zone basis. Zone C, which we said it's only shale. You see, it's practically high neutron because of the shale effect, and the shading is on the lighter part of the measurement. So now I know where is my reservoir. I know this is my cap. I know this is my water zone. I know that the most of the data that I have is sandstone, I mean the target zone. I can now move away into the quantity and start performing the formation evaluation. So to do the formation evaluation, now after the plots, you will have a couple of tabs, and you will have your petrophysics tab. So the petrophysics tab will have a various modules, which we called, starting from the QC, the tabs you will need to QC your data, which is the environmental corrections, the mud computation, the bad hole flags, or any custom flags that you want to flag in your data. For example, you have the caliber bad hole flag, the DRO bad hole flag. And then you will have your quantity, which is the conventional log analysis. You will have different methods from the shale volume, porosity, and saturation. If you want to use calculate lithology, which is, to be honest, this is not a reliable method to calculate the lithology, but you will have it anyway. And eventually, you'll have your summaries to summarize your results and report them accordingly. And that's about it. Next, you will have the quantity Elon, which we will get into after after this part, and some advanced methods like the thin bit, NMR, K-mode, 3D petrophysics, time lapse, and K-saw measurement. So now that I identified my data, let me also look at the caliper and see if I have some washout zone, which apparently I do not have. And full disclosure, this is, by the way, this is a training data set, so everything here looks perfect and in line. And of course, your actual data set will look much more messier. However, these principles should still apply. I mean, you should be able to see the separations. You should also be able to see your resistivity response against pay zones and so on. So whenever this, I mean, whatever is it a training or actual data, it should, I mean, it should act the same. So now, as I mentioned, this is the most important part, because whatever we will be doing next is practically a data entry. You can bring your 6-year-old brother and just tell him, do this, do this, do this, do this, and they can do that without any issues. Yes. Yes, please go ahead.
Hello, sir.
Yes, please.
Side. So, sir, I have a question. For example, if you have some uncertainties in our data, like the washout, breakout, or something else, so how should we QC and rectify our logs? For example, gamma, density, and neutron. When we have the uncertainty due to the washout or some another problems within the wellbore. So can you please show us with an example in this training data set?
Okay, in this training data set, it's not possible, but whatever I can show you on a recent well that I was working on, just give me a second here. Okay, just let me open the plot in a minute, because I worked on a previous project before, and there was a lot of issue. This is a petrophysical analysis, and to be honest here, I use in this petrophysical analysis, this is the advanced zone. It's not, so this is a washout zone. That's a washout zone, for example. You see the caliber, the gray shading here. This is practically going out of line. If I compare my neutron density, the red and the blue measurement, below and the above this zone, you can see the difference clearly. I mean, for example, I do not have 50% porosity. That's not possible. So it's clearly that my measurement here is affected. It's from washout, from the pore conditions, from so on. So what I did here is, we usually, when we take the sonic data has a much deeper depth of investigation compared to the shallow measurement of the neutron density. Of course, the resolution for the sonic is not the same as the neutron density. So what we did here, in this specific zone, or whatever zone that looks like it, for example, we also have one here. We have a couple of zones that has washout. What we do, we tell the software that for the first step we do is based on the caliper or based on anything. We open the quality. We can open a quality flag here. For example, you can pick about the whole flag using the caliper. You will get this window open asking you about your inputs. So my input here will be the caliper, and you will have a grayed out input, which is called the bit size. This is, if you have a bit size, you can add it. If you don't, you can just input type it. Write it down. So whenever I open a workflow, I will have this workflow manager here. And inside the workflow manager, I will have as much workflows as I would like. And this is the working space for my workflow. So all I need to do is bring the data set or the folder that I'm working on. For example, this one. This is my input. This is the zonation. If I want to use different inputs or different parameter for every zone, for example, we can dive into this later, and then we will have here, for example, my bit size. I did not insert it here, so it's now asking me the bit size in this one. So let me read the caliper measurement. How much is it reads? This is a 12¼ inch section, because the caliper is practically reading 12¼ and so on. So if I go back, mention that the 12¼ inch bit size, and the cutoff is, you can identify it as 0.5 inch, 1 inch. It will depend on you, the interpreter, eventually. So whenever you are done, you can go up. You will have this display or save and display. You can pick save and display. Click on the run. Okay, so there is no flag here because this one looks perfect, but eventually it will let's see here, just change the parameter just to show. See here, this is 1.1 now, because the measurement is reading 0.1 above the 12, for example, 12.25. If it's read 12.26, it will show you a flag. So this is what your flag will look like. Let's change it into more reasonable value, just to test. So for example, we can have this. Okay, 0.3. Okay, so for example, you will see your flags in this matter. After that, you inside the workflows, you will have the options to tell the software, look, if we go back to this example, look here, for example, you can tell the software, in this zone, do not use the neutron and density as a porosity measurement. Instead, use the sonic. Because again, the sonic will have a longer depth of investigation. We usually process the sonic too, so we will have more confidence in it. So it's a matter of pick and choose. You can pick another input to rely on in this zone or the washout zone. There are many methods. So I will go on with this just to show an example. But to be fair, in this example, we do not have any washout, or we do not have any bad hole to carry on. But just to finish the example, I will use this as an example for a bad hole, and then see how we can use different methods when we have a bad zones. So I really hope this answered your question. So after identifying your bad hole or whatever data issues you might identify, like environmental corrections, mud calculations, and so on, you can move on with the calculation, with the different calculation. The next step here, we will have the porosity, or sorry, V-shell. And you can either use different methods like the combined methods, and you average those, or you can use any separate methods: gamma ray, neutron density, spectral gamma ray, different charts, and so on. So let's go with the combined methods here, and let me quickly use the neutron density and gamma ray. So gamma ray and density, I'm just looking. Density, okay. And the neutron, porosity, okay. So after the bad hole, now I have this opened, the shell volume, and I have my inputs here. Now let's, again, if I want, I can add zonation to use different parameter for each zone. For example, if I want to treat zone B in a different way than zone C or zone D and so on, I can add zonation from here. You just pick your zonation. Let's see, I want a zone. I just want to solve for zone D and zone C. That's it. I just want those zones. So you can go. Sorry, this is the workflow again. You go stratigraphy, zone C, zone D. I deselect everything else, and then I can use this tab here to, now I have zone C, zone D, and the software will not solve for any other zone. And I can use different methods for every zone. Sorry. In the next step, I will have the method selection. So the availability of these methods will depend on how much input you have given this the workflow. For example, if I remove the density from here, I should not be able to see the neutron density. If I add the sonic, as an example, if I add the sonic compressional, I will see different, like sonic density, neutron sonic, and so on. Whatever method I like, or I would like to use, I can just select it. If I do not, I just can remove it. Now let's move on and see what we will have here. Okay, so first of all, we will have the gamma ray. Now, if you remember the gamma ray equation, that's good. It's the, I will need the maximum, the minimum, and the log reading itself. And for anyone who's doesn't know, if you forget about the gamma ray equation or anything in particular, not just the gamma ray equation, just use a click one, and you will have your the whole methods here. And for example, V shell from gamma ray, you will have all the equations, all the inputs, all the outputs, and so on, and what you will need to be using. This is, by the way, not not applicable only to gamma ray. It's practically for anything you are using. If you have some questions or you need some further clarification, you just need to click the F1 button, and you will get the physics, the theory, and how to use it. So that's just a small tip here. Now, for this equation, we will need the minimum and maximum gamma ray and as the gamma ray methods. So I can go back to my log. Let me close this one. And I can either use a baseline to see my minimum and maximum. Let me compress the log. So, for example, I can use the 25 as my minimum gamma ray, and then move it to 80 or 81 as the maximum gamma ray. However, I mean, this can be tedious if you are dealing with 2,000, 3,000 meter, or even 4,000 meters. So you will also, in the workflow, have this histogram here that will show you the data distribution as in a histogram shape for the gamma ray. And from it, you can move your line and, okay, this is my minimum, this is my maximum here. And if you don't want, you can use your histogram in this shape. Just change the display, and whenever I'm done with the histogram, I can go back into my Techlog, and you can see that my minimum and maximum have changed accordingly. Now I can do this on a zone by zone basis, or I can use it in overall. So just for the sake of an exercise, for this exercise, we can just leave it at this. We will also here have the second method, which is the let me change the view, the neutron density cross plot, the same cross plot that I was displaying, which is this one. Just let me remove the zonation. It will use this cross plot to calculate your shell volumes. And similarly here, okay, what you will need to do is identify your endpoints, meaning that you will need to identify your neutron in matrix, neutron in shell, your neutron in fluid, and similarly with the density matrix, density shell, and density fluids. Now, your matrix and fluid readings for the neutron and density should be known. Why? Because, okay, if you're having 100% matrix, it means that you have 0 hydrogen index, and your measurement should be reading 0. And similar goes to the fluid. If you have 100% fluid, meaning your hydrogen index should be equal to 1. So your which means that you will only need to evaluate your shell or your shell readings. And for the density, depending if you are in a limestone or in a sandstone, you use the density associated with the matrix. Here we said we have a sandstone, so sandstone density is 2.65. The density of the fluid is 1 or 1.1, depending on the fluid that you are using. So similarly, you will need to identify your density in shell. In order to do so, you can use the workflow here to open the workshop. And now you will have this triangle that will have your matrix readings. It will have your fluid readings, and then you will have your shell. So all you need to do is move this shell line into this shell point into your shell data cluster, and you should be able to, read it properly. So this is the wells data set. Okay, now let me filter, or basically this is my shell cluster. So all I need to do is move it, and can use it here, or okay, let's use it in here for the sake of this example. And now if I go to my workflow back, I can see that my shell line is at 0.4, and my density is at 2.35 for the explanation. So this is it. This is my density method. This is my neutron method. Now we can go to the final one, and in the final, it will ask you to tell the software which methods from these you would like to use. Of course, we haven't seen any results yet, but we can save and display. QC the results, and then we can go back to the workflow and ask them on which method we would like to use. For example, we have the V-shale selection here. We can either say I can tell if I can tell it for zone C, just use the gamma ray. For zone D, just use the neutron density. Or I can tell it for zone D, just use both. And sorry, and then use the final V-shell. What I can do also, I can use the bad hole flag that I calculated from the previous step. Now I will have use flag option available for me. So if I tell them use the flag, which V-shell I need to use if the flag is 1, meaning which V-shell I should be using if I'm having a bad hole. So you can tell it that use just the gamma ray, because the neutron density will be very much effective. And then eventually you will have this averaging method, which we will have minimum, max, mean, median, or whatever. All the mathematics behind them are available also in the help file. So whenever we are ready, we can just tell it that go ahead and calculate. So these are my results. This is my V-shell gamma ray. This is my V-shell from the neutron density, and this is my final V-shell based on the minimum calculations. That's about it. As you mentioned, all I needed to do is just enter the values, and this is the results. Now you will see a high discrepancy between the V-shell gamma ray and the V-shell neutron density, which means that we will need to decide which one is better, or why there is a discrepancy or not matching. We usually rely more on the neutron density side unless we have a very high shell volume. But yeah, just if I want to just use the neutron density, I can just go back to the workflow and tell them that in my zone C, just don't use the gamma ray, just the neutron density. And save and display. Now just let me. Okay, zone C, zone D, neutron density. No, okay. Okay, and that's about it. And now after calculation, if I go back to my data set in the project browser, I can see the outputs are there. The V-shell gamma ray, the V-shell final, the V-shell neutron density, and I can use any one of those into my subsequent workflows. So this is for gamma ray. Let's move on a bit faster, because we still need to cover the more advanced one. So the next one will be the porosity. You can use the porosity here. Similarly, you can use the neutron density. You will have different methods for effective and the total porosity. So let's go for the effective neutron density. And here it will ask you for the shell volume, so that it will kind of also use the shell volume to calculate the effective porosity. So that's my calculations here. And all I need here is to identify which tool I am using. And I also identify the shell value and the neutron value for the shell value for the neutron, and then density, which we already did in the neutron in the shell volume step. So you will see the same values that we had from the previous step. So once we are ready, we just click save and display, and okay. Just let me clean up my window here. For whatever reason, it is opening a different workflow. Okay, it was on a different. Okay, now save and display. And these are my inputs, and we will have the phi t and the phi e. The phi t is the total, and the phi e is my effective porosity using the shell volume. Similar to the gamma ray, I can use different methods and eventually use the final one to average and min-max them accordingly. And finally, we will have the saturation here. You see, we will have different methods. We will go to RG. Here, it will ask us for a resistivity and a porosity. So let's go with the deep resistivity. Deep resistivity was deep R, and porosity will be for, I'll just use the phi E. Phi E, neutron density, and that's about, okay. Now, for the porosity part, I will be needing the RT parameters. So just to reiterate on the picket plot, I can use this here. It's in the workflow, the first option in the toolbox. And this will be my picket plot. So what I will need to do is go back into the log, see my water zone, which I already identified back during the QC stage. So let's pick this zone as my water zone, and then go back to my highlight this zone. Now go back into my saturation RT or RT, sorry. Now what I can tell the picket plot show me only the highlighted zone. Now, if I go to properties, I will see A, M, and N, and RW. And I can either change the M to, you see the line will be moving. And I can fix the RW and changing these three until I get a match between this line and the cluster of the data. So we are good. Yes. Yes, Hadi?
Just please, when I want to determine the porosity effective,
Yes.
and I want to change the value of density matrix, where I can do that?
If you want to change the density of the matrix, you just in your density of the matrix, I mean, it was already decided here. You remember this density neutron method? You just need to change it into this is 2.65. This is the sandstone one. You just insert, if you are in a dolomite, you add the 2.87, and if you are in a limestone, you add 2.7.
Yes, that for shale volume, but I want for effective porosity.
Yeah, it takes the parameter from this one, and it will back. By the way, the effective porosity here uses the chart. It does not use the density equation. For the density equation, you will need to go to the porosity, and just pick the density. And once you pick the density, then you will have the Robbie matrix. Let me just move this window here. You will have your Robbie matrix and your Robbie fluid.
Yeah.
But this equation uses the charts, which is these charts only.
Okay. Thank you.
So yeah, there will be no the matrix one. But yeah, for the porosity density, you can use the 2.71, 2.81. And we will get to this point also later. So whenever you are done with the RT parameter, let's just change it for the sake of the exercise. If I go back, you will see the RW is changed, the ANM fixed. All I need to do is click Save and Display and go back to the workflow, and this is my saturation. This is my SW. Now, I also like to use this type of shading to highlight the oil and water. Now, if we reflect back on the results that we got, this is my SW, this is my saturation. This is what we said we should be having before even starting the exercise. So that's what I meant by this workflows or these softwares are just a tool to help you, reach your end goal. So whatever results I got, it's practically the same things that that we said we will have before even starting. And this is where the power of the this is the power of the software, or the the knowledge before the software. That's why okay, so practically this is it for the conventional log analysis. Again, this is, you will have a set of equations, and you are following these equations to reach your end goal, which is calculating the saturation. These are exactly what they taught us in universities in terms of formation evaluation. It's very basic, but I'm not very fan of it because they are not as powerful as what we will speak about next, which is the advanced or the quanti-Elon formation evaluation. So that's we call this the conventional or the deterministic. And let me highlight some of the issues here. For example, if we go back to the density thing, and we said we need to assume the density of the matrix 2.65, 2.71, 2.81. The reality, or one of the major issues that we will be facing in reality, a density matrix will not always be 100% pure sandstone, 100% pure limestone, or so these 2.71, 2.85, 2.65, or whatever, they does not represent your actual environment. Your environment will always be a mixture of different type of matrices. That's the reality. And the assumption that we are putting here will add some uncertainty on your results. And similarly with the V-shell, V-shell can be affected by many things. Radioactive, sometimes you will have a matrix that will have a high V-shell, high radioactivity. So practically the high gamma ray will not always reflect your actual shell volume. That's a fact also. So these methods here are easy to follow. They are nice structured workflow that we can follow up until, but they will have some uncertainty associated with them. And this uncertainty cannot be dealt with in any case, unless you will have some sophisticated tool. But if we are talking about a sense of conventional logs, then you will have to take this uncertainty with you and live with it, to be honest. And this uncertainty will eventually affect your oil in place and your reserve estimation eventually. So this is, again, easy to follow and to understand methods of formation evaluation, but it's not powerful. It does, all you are doing is following a couple of equations, and you do not have an actual control over the data. That's the issue. So before I move on, Mohammed, we still have the quanti-Elon. So I don't know, what is your suggestion? Should we move on, or we can reschedule?
As you prefer.
I'm okay with both options. So
I think we can continue if you.
I don't mind. But just in case, because the second part is a bit more sophisticated. So I don't know. If you guys if you want to reschedule for tomorrow to finish up the second part, or you want me to finish now and close this session, that's up to you. Okay.
Okay, I think we can.
Okay,
continue.
that's good. Okay, so this is the conventional log analysis. It's easy. It's nice to have, and It's practically the same workflow, whether you are using Techlog, whether you are using Geolog, whether you are using any interpretation software out there. So the next part is what we actually use when we do formation evaluation, which is called the elemental analysis, or in Techlog, it's called the quanti-Elon. So in quanti-Elon, we do not solve on a step-by-step basis, meaning that, and in similar, or in another word, we do not solve for petrophysical properties at first. So we do not just go and, okay, we do the shale volume, we do the porosity, we do the saturation, and that's it. No. Here we treat things a bit differently. First of all, with what we solve for here, instead of petrophysical properties, we will eventually get into petrophysical properties, but what we are solving for here is practically volumes. Instead of petrophysical properties, we are doing volumes. Volume of clay, not shell. We are using volume of clay. Whatever clay we are using, or volume of sand or quartz, volume of calcite, volume of dolomite, volume of fluids. What fluids? Volume of oil, volume of water. So we solve for volumes instead of, and these volumes eventually are we take these volumes and convert them into a petrophysical properties. And the solver, or the, let's say, the evaluation here, which we called a non-linear simultaneous solver, meaning that whenever I click run, you saw me clicking run visual, run porosity. Whenever I click run, by one click, I should be getting everything in just one click, which means that it will be very hard to follow the process and tell what really happened during the calculations. So this is practically how quanti-Elon works. Again, here it's a non-linear solver, so it's a non-linear, and it's done simultaneously, means in just one click. And here it's comparing it to the other programs, which is the deterministic solver, which is practically what we discussed in the conventional log analysis. So here it's just a reminder that the quanti-Elon, as much as sophisticated and as much as advanced it looks like, it will not do magic. So eventually you should be controlling the software, and you should be able to get the output you need out of it. Based on whatever result that you are having. So let's just go through the specifications of the software. So basically, it's a simultaneous solver. So simultaneous means it will solve everything in one click. And eventually, after this one click, you should be able to see the results and tell if these make sense or not. If they do not make sense, you need to go back and figure out what is causing the discrepancy and fix it accordingly. So, for example, if you, as an interpreter, do not see, for example, limestone in your data, and your Elon showed you limestone, you need to identify what is the cause of this and fix this accordingly. So how does the Elon works? How does it work eventually? It works on the working, or the physics of Elon works based on 3 different letters or components. We have the T component, or the T vector, and the R vector, and the V vector. The T vector is practically your inputs. We call it the tool vector, your logs. So in Elon, you will take your logs all at once, not gamma ray, then neutron, then density. You will take everything, and these logs, you will take them, and the response of these logs should be known to you and to the software under a certain environment. For example, you know that your density reading is practically the density reading of the combined fluids and the matrix that are in the formation, meaning that if you have, just an example, if you have 50% sand and 50% water, that's just an example. I know it does not exist in real life, meaning that your density reading, your log reading should read 0.5 multiplied by 2.65 plus 0.5 multiplied by 1, which is the density of the fluids. That's the response vector. It means that every measurement should will have standard reading for every component. And whenever I show you this in the software, it will make more sense. And finally, you will have your volume vector, which is the volume that you are trying to solve for. For example, you are trying to solve for the clay volume, the sand volume, the calcite volume, the water volume, the oil volume. So your volume components. So what Elon will do as the first step is take your logs. It will take their response parameter or response equation, and it will solve for the V, which is your volumes. After which, as a QC measurement that Elon does for you, and you will need to figure out if that QC is right or wrong, Elon will take your volumes, it will compare your volumes with the response parameter or the response vector for each volume, and it will recreate or reconstruct your input logs. So what you will have your volumes and you will have your reconstructed tools. And whenever you will have a match, or let's say less discrepancy between your reconstructed logs and your input logs, it means that your error reading, you will see some error reading whenever you do an Elon is at minimum, at its minimum. So that's how it works, and I really hope it will make more sense whenever we go to the workflow. So this is actually what is happening. So you will have your logs, gamma ray, neutron, density, resistivity, practically any log that you can think of, not just these. And you will have your every log reading in 100% component or the response parameter for every log for each volume. So for example, the gamma ray in clay, 100% clay, the gamma ray in 100% quartz, the Robi, and so on. So you have your measurement, your parameter, and one final thing, the software or Elon does not work in some random way or some crazy way just to get you your results. It will have its own its own constraints, or let's say some rules that they will have to follow. Otherwise, you will start to see some crazy things going on. So, for example, one of the rules that that the software have, that all your volumes eventually should equal to 1. So unity. your volume of fluids, the fluids volume inside of the shallow and the uninvaded zone should be the same. I mean, as a total volume of fluids, meaning that if you your deep zone in terms of porosity should not be changed whenever you go deeper, because I mean your distribution of the fluids will change, but the total volume should remain the same, and we can discuss these volumes. So all of these will combine together, and you will use the solver into getting your volume. So here, for example, the quartz, illite, calcite, bound water, free water, oil and gas, and these will be your volume. And eventually your water volumes here, the bound, free, oil and gas, will be converted into porosity, and your matrix volumes will be converted into a lithology, and your oil volume will be converted into oil saturation, your gas volume will be converted into saturation, and so on. This is after you finish your Elon. So this is the response parameter. It will show you some example on it. Here, by the way, your response equation, you will have two types. The first type is the linear ones, which are, for example, the density, gamma ray, and then you will have some non-linear equation, and then I will explain the differences here. So let's see, and okay, the linear equation or even the non-linear will act the basis on it. It will be the volume of the component plus how is the ideal, or what is the standard reading for the tool for every component. For example, let's say this is an example. Your density, your bulk density, the log reading, it will eventually be if you, let's say, take it into a component level of reading, it will be your density of a quartz multiplied by the volume of that quartz plus the density of the illite multiple for the volume of the illite plus the density of the water, or multiplied by the volume of water, and so on. So it will be the summation of the component that the density is reading to. This is your measurement of the density. This is what we call the linear equation, and we can add as much. We can even add linear equation from our knowledge, for example. So that's an example here for any linear one. So for example, the density log here, it will be the 2.65 multiplied by how much volume of quartz I have, plus 2.45 or whatever clay I'm using, and so on. So that's basically the linear equation. The nonlinear equation, it's a bit different. Not in a sense that it does not respond or it does not have the same response as the linear, but it means that the nonlinear equation will have the linear factors, which is the component, plus the reading of that component, but it will also have some external factors that might affect the measurement. For example, let's go to this one by one. The sonic measurement. The sonic measurement, it's okay. It's the linear response, but it will also, let's say, affected externally by the combustion factor. The neutron will be affected by the salinity. Because the salinity will increase or decrease the absorption accordingly. Similarly, the conductivity and the resistivity. This is so if the fluid measurement is affected by some external factor, or the rock was affected by some external factor, aside from the volumes of these readings, then you will have a nonlinear equation. All the nonlinear equations are practically programmed into the quanti-Elon, so you don't need to worry about them. All you need to just know about them. So this is what Elon will looks like when you open it in your Techlog. So you will have your input and you will have a catalog of component. And you will need to tell the software which component you want to solve for. So a knowledge or a petrophysical knowledge here is a must, because you cannot just go it's not, for example, this is not a shopping list where you okay, I want this, I want that, and I don't want this. Whatever you select should be present in the formation, because the software will not know that, okay, no, this is not present. The software will solve you no matter what you input or you select. So for example, here you should know what type of matrix that or fluids you need to solve for, and you just need to select by clicking yes or no. That's about it. It's very easy. And here you will see the standard. This is the R. This is the response parameter. So practically, if we solve for L-light, this is how the density should read if you have 100% L-light. This is how the neutron should read if you had 100% neutron. This is what the compressional or the sonic should read, and so on. If you have 100% L-light, meaning that you will have zero porosity. If you have a gamma ray, then your L-light is practically the type of clay. Here you do not deal with the V-shell. You will need to identify the clay type and which clay that you are using. Similarly with the quartz, with calcite, with coal, or whatever you select, your water, and so on. So that's about it. Some values, you see some green readings here for the example. This is the nonlinear equation. These are the nonlinear equation. These will come from, before you start your Elon, you will need to insert your pressure, your temperature, and then you insert your resistivity of mud filtrate, and resistivity of mud cake. And this will give the standard of the reading for every nonlinear reading that you will be having. So, and if you are not happy with any reading that is present here, you can change it quite in a bit. But I mean, if you are not an experienced petrophysicist who know what to do here, then I recommend keeping these for default. So again, as I mentioned, Elon will have works in a wonderful way. It's a very powerful tool, but again, there are some rules that keep the software in check and keep you from getting some unwanted or some incorrect results, physically. For example, one of the rules that your total volume should equal unity. So you cannot have volumes and you add these volumes and then you will get 1.1 in total, because you will not have 100% and 110 in terms of volume. They should always be at 1. This is okay. And similarly, your volume of fluids, no matter how much the fluids in the flushed and the unflushed zone, the total. I'm not referring to the volume of oil or the total of volume of the fluids in the invaded and the uninvaded zone should always equal. They should equal each other, and these will eventually be converted into the porosity. Yes, your distribution may vary from the invaded and the invaded zone of the fluids and what and in terms of water and oil, but eventually they are the same if you sum them. Always verify these constraints. Okay, they are built into the software, but you will need to look into it. And there are some constraints that are available, but they are also optional for you to follow. For example, here. You can tell the software that my total volume of fluids, meaning the porosity, should not exceed I mean, this is something optional. You should not exceed 0.15. If you add this type of constraint, it means that you tell the software that your volume of fluid should, or your porosity should not exceed 15%, and the software will follow. It's not particularly correct or anything, but you will have the options to do so, and so on. You can also tell the software that you will have a resistive invasion, or let's say you will have conductive invasion, just to verify how much fluids that you will have. So you see water-based mud constraint that you will tell it that in the shallow zone you will have more water because you will have a water invasion, or vice versa if you have oil-based mud. So that's some of the rules, and eventually, as I mentioned, the final step after you get your volumes is that your Elon will take your volumes, do a forward model or back calculations to recalculate or reconstruct your inputs, your log view, and then you can see the match between your reconstructed logs and your actual logs. And whenever there is a minimized difference, then you will have a less error. Less error does not mean correct results, but yeah. Sometimes you will have more error and more accurate results, but again, this will require knowledge to verify. One more thing here, you will have, as I mentioned, you will have your input, you will have your volumes to solve for, and you will have your outputs. So here you will have, if you don't have enough inputs, then it will mean that you are in undetermined system. The software will tell you that you are in undetermined system, and you might need to bring more input, such as some local knowledge or some external tools. If you have enough inputs to solve for your volumes, it means that you are in a determined system, which is practically the best case scenario. And sometimes you have a lot of logs or a lot of inputs, and they might be even more than your outputs. In this case, you will have over-determined system, but this will not always be a good case to have, because, for example, if you have, let's say, sonic neutron density, and you want to solve for porosity, you can, for example, go with the neutron density and get an answer, and then you can go with the sonic and get a different answer. So an over-determined system can also be a problem, because it can misguide you into having results. You need to know which inputs you want to rely on and which inputs you don't want to rely on much. And to that, we will have two types of things inside. Whenever we are dealing with inputs, these types are called uncertainties and weight. So whenever I bring an input in Elon, I will have next to it some uncertainty, and I will have an input weight. So, for example, if I want to use the thing more, for example, let's say if I want to use the bulk density more than anything else here, just an example, I can either increase the weight on the density to rely more on the density, or I can decrease the uncertainty on the density. I can use either way. What I recommend, I mean, for all of you here, is always try to utilize the input weight and steer away from the uncertainty. Why? Because the uncertainty here, for example, this is a bulk density. The uncertainty means 0.027. That means that my log reading, what I see in the log view, or the what I read from the log, it means that this value will have a plus minus 0.027 gram per cc of uncertainty. This is decided, or this value was decided by the engineering team that designed the tool. So they pretty much know better than us in terms of uncertainty, how it reads. So unless you will have some reference paper, sorry, reference paper or some specific cases you want to change on the where we can use the change the uncertainty, I advise you, if you work on a real-time data, inshallah, sometime in the future, or if you work on it in a real time, if you're working, then I recommend you just stick with the changing the weight. And for example, here, if I have a neutron density and sonic, and I don't want to use the sonic as much as the neutron density, I can keep those as 1 and then decrease the sonic into 0.3, 0.1, or even turn it off. That's a possibility too. If I want to use the gamma ray more to help me with the shale volumes or the clay volumes, I can just increase the weight from 0.3 into 1. That's also a possibility that I can take. So you can either do both, but unless you are very much experienced with the uncertainties, I advise you to go with the weight. One final thing here to discuss is you will see also something called invasion or unflash factor. One of the great things about Elon that it knows how much depth of investigation each tool has. So depending on that and your invasion profile, how much the separation, how much the resistivities and so on, it can tell how much of your reading in the invaded zone and how much of your reading is in the uninvaded zone. And you will see a window, 0 meaning that you're reading in the invaded zone, 1 meaning your value will always be something between those. Unless you have some deep invasion, then you will have a 0, and most cases it will not be so much. So that the message of this slide is that the software also knows how much the depth of investigation of these tools are, and it can account for that as well. So again, some of the Elon requirement, to summarize what we said here, or some of the things that the software will assume and it will not correct for you. For example, in terms of QC, Elon will always assume that what you entered in the workflow are environmentally corrected. So you cannot expect it to correct this for you. So if you want, always run the environmental correction workflows before you go ahead and do it. Of course, the knowledge of the logging physics and response in terms of depth of investigation, the response parameter, it's all embedded in the programming of Elon, and similarly with the fluids. You as the user are also expected to know how to QC the data, how the tool interact with each other, and how the tool physics works. And you should have an idea of what you want the results to look like before you even run the Elon. Similar to what we said about the quant Elon, because again, garbage. If you input garbage, you will get a garbage. That's the case. Okay, so the strength of the software, again, it's a simultaneous solver. So you will see me just click and get results with just an instant. It can handle any solvable model as long as you don't have underdetermined, and you can insert your external knowledge to it if you know something that you don't have on the logs. For example, if you know you have some volume, and this volume is, let's say, a percentage of another volume, you can add it as an external knowledge to strengthen your Elon. And it has an extensive tool database, meaning a lot of the industry tools are programmed into the Elon. You can handle every log from the conventional to the NMR to the spectroscopy, and even some external tools. Then you can handle all of these. And again, it honors the depth of investigation for the tools, and you'll have the parameter initialization to ensure that you will have all the invasion parameter and the nonlinear equation are set for you before you even start. The weakness of the software, again, the software will not tell you the results are correct or incorrect. This will be on you. And you can add linear equations externally as an external knowledge, but you cannot do it with a nonlinear equation. So that's one of the weaknesses of the software. If you want to add a nonlinear equation, it will not be possible. You will need to do some programming. So again, one last warning, you are interpreter, Elon is just your assistant. A lot of petrophysicists I know are just dealing with doing whatever mindless work in Elon and then come up with the results, and then it will be very difficult to track these results unless you start from the beginning. So okay, this is the Elon in the software. We will just I will not talk much here, but this is what the final results should look like. Now I will move away from the slides and go back to the software. Okay, okay, let me cancel this because this is the log. We will use the same log here because we want to compare results, and we want to compare how the log works. So Elon, quanti-Elon is practically inside the petrophysics module or the petrophysics tab. It's next to the quanti. You will see a lot of methods or tabs in the quanti part. But since everything here is in the quanti-Elon is in just one click, then you will see less available options for you. So let's click on the quanti-Elon, and we will have all these workflows. You will have your initialization here. In the initialization part, you will need to add your resistivity of mud filtrate, and resistivity of mud cake. These parameters you usually get from the drilling team, so these are very easy to get. You will also need to know about the resistivity of water or the salinity of the formation. Any one of these will help you eventually evaluate your zone. If you do not know this, you refer back to the picket plot where we used to identify Archie parameter. So you need to know RW for an instance. If you know this, then you are good to go. Then after the initialization, you will just get a we call it salinity temperature parameter, which will help you identify set the parameter for the fluids. And your nonlinear, practically you set your nonlinear equation. After which you will have the quanti-Elon. Quanti-Elon, you can do as much as Elons as possible. You can do one for bad hole, another one for bad hole, and eventually you can use these combined models to combine into one final Elon. And for example, the methods where the method I follow to use the Elon here, I go create an Elon, assuming everything is okay. I don't have anything. Let's assume I have no issues and all the data is perfect. So I do my Elon here. Then I build another Elon, assuming that I have everywhere is rubbish. Poor washout, all the data is affected. Then I use let's say some condition to combine the two Elons. For example, I can set the bad hole flag that I calculated early, or I use the caliber to calculate a bad hole flag, and then ask the software if I have a bad hole, use the bad hole Elon. If I have a good hole, use the good hole Elon. Then eventually you will have the post-processing here where you just click save. You don't need to change any parameter or anything. And it will convert the volumes into petrophysical properties such as porosity, effective porosity, shell volume, lithology, permeability, and even saturation. So let's start with the initialization here. So let's see, what do I have? A temperature and pressure here. Let me see my data. I should be having a temperature and pressure values. So bottom hole temperature, VHT. Okay, we have a temperature. And looks like I don't have a pressure, but you should always have that. Anyway, for the sake of the exercise, you will need a temperature, pressure. Porosity, you will, I mean, it's not necessary. You just need to give an average value. For example, what average value in the field of the porosity in the field that you are working on? Just some average thing that you will be needing. So bottom hole temperature, I don't have a pressure. If you don't have a pressure, it will calculate it for you, by the way. So let's bring the data set here. This is my input. You will need to add the values of the mud filtrate temperature and mud filtrate resistivity or the salinity. So let me add 0.03. Just sorry, this is temperature. 0.025. What the hell? 0.05. Okay. Now I don't need to add the salinity because it will use the temperature and the to calculate the salinity. Here I can just similarly, let me just add values for the sake of the exercise. Mud weight 1.1, average porosity 0.15, and whenever you are done, you click and save and display, and you should be getting a group called sal temp where you will have your fluids parameters. Now, if I want to know these values, if I have an actual case, you should always look into the headers of the information you are getting from the field. For example, let me show you a case of an actual data. Okay, this is an actual log. Now, all these values you should be looking into. You see, RM temperature, RMF, RMC. So here I want the RMF 0.5. Yeah, that's just an example here to highlight. And whenever you are good, you click save, and now you are ready to do the Elon. So let's go to the Elon. You see here, Elon will not force you to pick some parameters. You are free. Everything here is grayed out. You are free to pick whatever resistivity, whatever logs you want to use, and leave out the rest. If you are in undetermined situation, the software will tell you. So I will be using the density, neutron, resistivity, medium resistivity, sonic, and I don't have a place for the gamma ray. So here you see there is no gamma ray. So there is UI, which is user input. I can add the gamma ray into it. And I can add anything here from NMR logs into spectroscopy logs into dielectric logs. And yeah, the list continues. So this is my Elon. This is my input, your zonation, if you want to do zonation. And okay, now we can delve deeper into the workflow. So these are my inputs. These are my uncertainties. Again, as I mentioned here, I do not recommend changing the uncertainties because these are set by the engineering team behind the tool. You will have something called uncertainty type, which is absolute and relative. Absolute meaning that my measurement will be plus minus the value. Relative, it means that it's a percentage of the value, meaning that this 0.07 will be the percentage of the uncertainty instead of fixed value. Input weight here, if you want to use something, you can either increase it, or if you want to use it less, you decrease it. So let's go, for example, for the sonic. If I don't want to use it, I can decrease it to 0.3, to 0.1, or if I don't want to use it as all, I can just, in the activation window, just tell it off or no. This is your type of equation, if it's a linear, non-linear, and so on. The tool type, for a neutron, it's very important to identify what type of a neutron measurement you are using. And so this is NFI, TMPH, IPLC, whatever tool you are using. So in this case, we have the NFI, which is the old mathematics neutron measurement. And the constant will tell you which tool that you are dealing with. So let's just move this out of the way. Neutron density, compressional. You see here, my gamma ray is not, it's a user input, so it's not defined. So let me go and search for it. So I will have a gamma ray here. You see, once I selected it as a gamma ray, my user input is changed into 0.3, and my uncertainty increased into 6. Meaning that if I have a reading of 150 gamma ray, it means it can either be any number between 150 to 156 or 140, whatever, 144. So that's how uncertainty work. If I change it into relative, the 6 will be 6%. So it means that my measurement will have 6% instead of 6 GBI. So that's your input weight. This is your uncertainty, meaning that you are telling the software that you will have some uncertainty on your results. This is your T for the T, V, and V. So this is your T here. Next, we will go and ask the software to solve for the V's, the volumes. So anything I want here, I can click on activate. And if I don't want anything or any volume, and you can click no. If you want to filter out, you can click and say which ones you are selecting yes for. You see here, I'm solving for these type of V's. The illite, quartz, calcite, water, oil, and so on. So we said we have 3 pillars, V, T, and R. And this will be my R. So what the software will use, it will take these T's along with the how many uncertain, it will give input and uncertainty for each of my tools. It will take their ideal response for every volume of these that I'm solving for. And these will be the volumes that the software will solve for. As simple as that. Now, how do I make sure that I'm using the right amount of volumes or the right volumes? You should either, for example, know your formations. If you are not, for example, let's say if I'm using an example of the south of Iraq, Mishraf formation. And Mishraf formation, I'm 100% positive that I will find calcite, so I will click on the calcite. I will also 100% sure that I will not find the quartz, so I turn off the quartz. And in some cases, that I might even find some, let's say, dolomite, so I can pick the dolomite on. So it will depend on your local knowledge. One way or a good start to pick your, because this is all about picking your volumes correctly. I can pick anything here and the software will just solve it for me without any issues. So one good way to to start with your picking is by using the mud log. You see, because during the drilling they take the cuttings, and you will have the mud logger, and it will give you your mud log for every formation, and what type of cutting description that you have. So you can take this as a starting point to take your volumes for every zone, and you can use the zonation, and you can use an Elon per zone, and you select your volumes. Okay, so here, for example, my clay is illite, so this is the bound. This is a wet clay porosity, and it will have some bound fluids in it, which will be eventually calculated into a bound water. Here is my RC parameter to convert the oil volume into saturation. So this will be A and M and N and so on. And here you will have some, if you want to add constraints from your, or add constantals, and for example, you can have your maximum porosity and tell it that I don't want my porosity to exceed 10%. It can do this for you, but again, that's not recommended. So that's about it. Whenever you are ready and your module is ready, you will see once I click on, okay, that's still not, okay, I need to save this. Okay, and then go back and display. That's it. You see? With just one click, it did all the solving. Everything is done correctly. These are my inputs here. And this is my outputs. So we will have the flush zone evaluation. We will have the unflush zone evaluation. This is my Elon cumulative volumes. This is my lithology volumes. And you will see this is my porosity after the evaluation, and here I have my saturation. You see here, I'm not quite very happy about the here because I don't see there is an oil here. I believe we need to fix it a little bit. So I can go to the special model and let's say 03 and display again. Yeah, this is practically because I used some random numbers here. You will always need better you see. And one final thing, you will see that the software did some sort of back calculations or forward modeling and reconstructed all my tools here. So you will see whenever I have a match between my actual reading and the reconstructed reading, it means that it will be shown as a, let's say, this yellow shading. So the more match I have between my modeled and my actual measurement, the less error I have. For example, here in the Cabrock, if we look at it, we have some slight mismatch. We have a mismatch in the sonic. So if we go into the error QC, you will see a larger error. By the way, this type of error is not something that we need to do something about, and eventually it will come to you as to do the actual QC and decide if your results will make sense or not. And just to emphasize on how much, again, you will need to have some good knowledge, or some knowledge on how to solve. For example, let me randomly select dolomite instead of calcite and resolve. You see, the software did not have any issue with it. It did not say this is wrong, what you did is wrong, this is not the correct way, it should have been calcite. You see, it just solved for it, and Even the error indicator is very low. So this will come to you to decide if you are happy with the results, because you see, all I do is a click and everything is in place. So if I'm not able to QC this properly, then I can get with some misleading results with some very nice low error, and I can send the incorrect results. Then a lot of question will be raised back to you. So let me go back to the call site. See, whatever you want something, you just want to click yes, and the software will not mind. So this is for Elon. All you need to do is identify your good logs, give them good weights, identify your very bad logs, and eventually you will need to identify which volumes you want to use on a zone by zone basis. Add whatever constraints you want. Make sure your mud parameter here are incorrect, because it will decide the endpoints for every log, and that's about it. If you are happy with the results, you just go to the post-processing, you add your we just add volumetric. Did we save? Okay, let me save. Okay, this is my quantity Elon. You add your volumetric into the workflows, and volumetric quantity Elon. I really hope you are. Okay, let me. Okay. You go to the post-processing. The post-processing is practically nothing. It will just, okay, took it. It will organize your results. Everything here is should be left as a default. And okay, there is something wrong with the software, because I should always I should not keep getting the first one. Okay, and that's it. This is my results. This is my permeability, shell volume, saturation, porosity, and lithology. Just one click. And that's it for Elon. So sorry for taking a very long time, and this is it from my end. If you have any question or anything you want to ask me, then please go ahead.
So thank you so much, Mr. Amin, for your time and for your expertise you have shown in this webinar. Much appreciated. Anyone, if you have any question, please write it down in the chat box, or you can raise your hand and speak up.
Okay. By the way, just give me 1 minute just to, I just need to open the door. Okay?
Sure.
Just 1 minute. Sorry. Please go ahead. Where can I access? Any questions? Anything? Okay. Okay, it is a general question. What do you think is the best way to advance my knowledge and experience? I mean, to be honest with you, you can read a lot of publications, you can read a lot of books or resources, but the best way is to it's a hands-on experience, and you deal with different type of data with different problem, and every problem you encounter and you overcome will eventually will be one step to increase your experience. Sir, when do we need to do normalizing? Okay, so practically for the newer logs, whenever we have new logs or we have a very new advanced technology, then we do not need to do some sort of normalizing, because we can do the environmental corrections. We can redo these. We can redo these environmental corrections at any time. However, when we are dealing with a very old logs and we encounter some discrepancies between the old logs and the new logs, then in this case, it's very recommended to normalize the old logs into the new logs to if we want to do some multi-well big studies, so that we can have everything set up together. How famous is applying artificial neural network to get a better physical like permeability in normal work? We do it all the time, to be honest. Like the multilinear regressions or some sort of core log, let's say, correlations. So we have a different, we have a lot of applications for the neural and AI workflows. I mean, every day they come up with a new workflow, to be honest. Even for Elon, by the way. I mean, we have the Elon now, and what we have, I mean, it's not like something we will have in the future. It's already here. We have an auto Elon, where, for example, for a certain field, you will do a lot of. You have done a lot of Elons, so you just feed those into the AI, so it will learn to do an Elon by itself for the future logs. So we have, yeah, we do it all the time. Yes, Himanshu.
So for the normalization, what would be the workflow that we use for the normalization? Actually, I do the geomechanical studies. So sometimes I have to work for the well field for the very old producing wells, for example, 1980s, 1970. So that time I have to do, for example, doing the geomechanical study, the normalization. So what would be the workflow for the normalization?
For the normalization, let me see if I can recall it. It should be somewhere here. Data harmonization, Python. It's somewhere here. Sorry, but I cannot recall the place. But I mean, the workflow is a standard. All you need to do is decision anchor. Okay. Okay. It's here. Well classification or decision tree. Something somewhere here. All you need to do is select the logs that you will need to normalize. For example, you want to normalize your neutron. It's the most common log that you will take to, or you do the normalization for. And you will have your reference normalization. You will pick some zone of some zone that is not affected by any oil or not affected by any bad hole. For example, a pure limestone water zone where you expect the typical zone. You select this zone as your normalization zone. You select your reference logs, which should be the reference logs, and you select your old logs as a normalized logs, and it can be done by just a click. All you need to do is decide your inputs and outputs and your zone of normalizing. Okay. This is the. You see, this is your normalization. You just put your input. Let's see. I want to use the neutron. Okay, neutron. If you have some bad hole flags, let me go back to the software. You see here, all you need to do is the type of normalizing, the endpoints, But you will need more than one well here to normalize. Otherwise, I cannot do it with just one well loaded into my. You should have 10, 15 logs, and you use this as a normalizing. Yeah, I mean, you can just decide which ones will be your calibration and which ones will be your reference logs, and that's about it.
Okay, thanks a lot, Sophie.
So no more questions? All good?
So I think that's all, and we don't have any question in the chat box. I would like to thank you once again so much for your time, and all attendees for their attendance in this webinar.
Thank you, Muhammad, and thank you for this valuable opportunity. So it was very nice meeting you, and to be honest, I live in Erbil, so we can do a lot of arrangement inshallah in the future, and hopefully we meet again in some some other event. So thank you.
That
and,
will be my pleasure.
No issues. So thank you, everyone, and have a nice evening.
Have a great night. Thank you so much.
Goodbye.